Hello, and today we're going to be going over all of the different motion graphs that we use here in honors physics. So specifically what we'll be doing is going over how to create and interpret graphs for position, velocity, and acceleration versus time. And then from those graphs, how to actually kind of figure out what we can learn from the slope of some of those graphs, and then the area from some of those graphs also. So let's get started. So here we have a blank graph, and we want to make a position time graph from these little statements over on the left. So let's say a girl's walking at 1 meter per second for 4 seconds. So she starts at 0, and after 1 second she's walked 1 meter, and then 2 seconds 2 meters, 3 seconds, 3 meters, so on and so forth. So we have a line right there for those first 4 seconds. And then she stops for 3 seconds, and so her position isn't changing. So I can just draw a line, position not changing there for 3 seconds. And then it says that she runs back home at 2 meters every second. So after 1 second, she's gone 2 meters. Another second, another 2 meters. So there we just kind of have a steeper line going down. And so here we have this position time graph, and all it does is tell us where this girl is in relation to 0. So that's the whole point of a position time graph. What is the object's position at what time? So when I have a position time graph, I can actually figure out the slope of each little interval there on my graph. And that's going to give me what the velocity is. So remember, slope is rise over run. And so for this first part, the red line right there, it goes from 0 to 4 meters. So there's a rise of 4 meters. And the time it takes is 4 seconds. Well, this gives me 1 meter per second. Which makes sense because now I have the velocity that it said that the girl went during that first interval. So I'm going to write 1 meter per second right there. For this green line right here, the slope of a flat line is always 0. Okay, so here I have 0 meters per second, which makes sense. It's not changing its position. And then for the last one, for the blue interval when she's going back home, we have she goes down 4 meters, so I put negative 4 meters, and it took only 2 seconds to do that. So when I simplify that, I have a velocity of negative 2 meters per second, and which also, again, it makes sense. She was going 2 meters per second, and that negative sign right there just tells me the direction. So because she's going back towards her 0 point, backwards, that negative tells me she's going backwards. Now, velocity time graphs are cool because they actually give us the exact same information that we had from the position time graph before for the motion of our girl that was walking around. It just is displayed a little differently. So how we look at it is during this first interval, when the girl is going 1 meter per second, she's doing that from time 0 to time 4 seconds. So on the velocity graph, I just draw that as starting at 0 all the way to 4 seconds. I say that she's going a constant 1 meter per second. And then for this middle part, from 4 to 7 seconds, she's traveling at 0 meters per second. That's when she stops, she looks at some clouds or birds or whatever, and she's not moving at all. So there, starting at 4 seconds all the way to 7 seconds, I just draw my line showing that she's moving at 0 meters per second, or in other words, she's not moving. And then the last bit, when she heads back home at 2 meters per second, I can show that. So at 7 seconds, she changes direction and rushes back home at negative 2 meters per second. So starting at 7 seconds and going to 9, I draw my line right there. And it's important to remember this negative sign right here. That negative sign just tells us direction. So this -2 shows up on our velocity graph because now that blue line is underneath the 0. And that just means that because there's a negative velocity, that shows that she's traveling in the negative direction. Now what's pretty cool is we were able to figure out this velocity graph from a position graph. And so it really makes sense that if we know the velocities, we should be able to go the other way also. We should be able to figure out what change in position happened. And the way we do that is by using the area under our line. So if we take a look at this first interval when she's traveling 1 meter per second, the red line right there, if I want to find the area, it's really important that we always go to the 0. So here's 0 right here. Okay, and so it's the area of this little rectangle. And remember, the area of a rectangle is length times width. So the area of that red one, its length is 4 seconds long. So 4 seconds. And its width is 1 meter per second. That's how tall it is. 1 meter per second. So the area is 4 meters. Now for this green line right here, makes sense. I can't find the area under that because it's on the 0 already, which kind of makes sense because if it's a velocity of 0 meters per second, she's not going anywhere. So she hasn't changed her position at all. Now for this blue one, again, it's really important that we always go from our line to the 0. So because this blue line is at -2, the 0 is actually up above it. So remember, this is a rectangle also. So that's length times width. And so we have 2 seconds long and a width of -2 meters per second to give us a displacement of -4 meters. All right. Now what this tells us is that during this first interval from 0 to 4 seconds, she goes forward 4 meters. That's the one in the red. And then she stays still for a while. Remember, this negative sign tells us the direction. So then she goes backwards 4 meters and ends up right where she started. Now we can also look at the slope of a velocity time graph. And this is a totally different graph, so don't get that messed up or anything. But I look at the slope, and that's going to give me the acceleration of an object, or how much it's speeding up or slowing down. So for number 1 here, what is the acceleration of this car at t equals 4 seconds? Well, 4 seconds is right here. And so I just go up this line until I see where it's at. So at 4 seconds, it wants to know the acceleration. So I want to know what is the slope of that line right there. Now this is a flat line, so we should know right away the slope of any flat line is equal to 0. So the acceleration at time 4 seconds is equal to 0. For number 2, to find the displacement of the car over the entire 8 seconds, that's when I'm going to be using the area under my lines. But to do this entire shape that you see would be kind of complicated. So I want to break it up into some simpler shapes. So we can make a triangle right here. Remember, the area of a triangle is 1/2 base times height. I have a just full-on rectangle right here. Let's change colors. Remember, the area of a rectangle is length times width. And then I have another kind of bigger triangle over here. That's again 1/2 base times height. And so I just need to find the area of each one of these pieces. And so the total displacement would be the area of the triangle plus area of the rectangle plus area of the triangle again. So we can do that. Area of that triangle would be 1/2, 2 seconds, and the height is 3 meters per second, plus length times width is 3 seconds long and a width of 3 meters per second. And then the area of that other triangle is 1/2, base of 3 seconds, height of 3 meters per second. And so my overall displacement, after I just add up all those little areas, ends up being 16.5 meters. So how do we tie all of this together? You know, going from position to velocity to acceleration, or whichever way you want to go. Well, there's really two tricks we need to remember: when to use slope and when to use velocity. So if I have a position graph and I want to figure out velocity from it, then all I need to remember is I will use the slope of that position time graph to figure out an object's velocity. Same thing where if I have a velocity graph and I want to know what the acceleration is, I will always use the slope of a velocity time graph to get the acceleration. So there's a pattern showing up. If I want to move to the right down this chart, I'm always going to use slope. Now the flip side of that is if I want to go back up the chart to the left, I'm always going to use the area under my line. So if I have an acceleration and I want to know how much something's velocity changed, I'll use the area of that acceleration graph. And if I have a velocity graph and I want to know how something's position changed, or its displacement, I would use the area of that velocity graph. So it's really important to remember this little pattern. Always, always remember.